Here's our second example. Feel free to press pause in the video and try to solve it by yourself. Part B we'll need the diagram for, but you can try part A on your own if you would like. But here we have a radar speed sign, right? One of those signs by the side of the road that tell you how fast you're going. It's 12 feet from the side of the road. The moment a car is 20 feet from the sign, so the distance from the sign of the car, the radar detects how fast that distance is changing. And our goal for part A is to figure out how fast the car is going. So for this one, we'll first draw a picture. Most of these questions are geometric, so a picture will be useful. So like here we have the sign. Here we have the road. The distance from the sign to the road is 12 feet. We have a car over here. The car is going towards the sign, otherwise the car couldn't see it. Right, which means the shape that we're working with, of course, is a triangle. In this triangle, these two lengths are variable because as the car goes down the road, both these lengths are shrinking. Therefore, they must have variable names. I'll call this one X, I'll call this one Z. Right? Both those have to be called variable names since they are changing. And we want to know how fast the car is going. How fast the car is going to be dx dt. Because if the car is going like 50 feet per second, then x will be shrinking by 50 feet per second. So how fast x is changing size is how fast the car is moving. And then the formula that we need to relate our unknown values will be the Pythagorean theorem. And so, once you have your formula, just like the first one, you differentiate where time is the variable. And then plug in your values. Now, we know that at this moment in time, z is 20. So we're trying to figure out dx dt at the moment z is 20. We also know that how fast the distance between the sign and the car is changing is 32. So dz dt is 32. But it's negative 32 because as the car goes down the road, z is shrinking. So it's a negative rate of change. We plug all these values in. The 2's cancel out. We don't know what x is yet, but we do because at this moment z is 20. And so we have 12 for one length, 20 for the hypotenuse, gives 16 for the other side, right? It's a 3, 4, 5 triangle times 5, or times 4. And then we just plug our values in. And simplified dx dt is negative 40 feet per second. But the car didn't say, what's the rate of change of x? The car said, how fast is the car going? And so for how fast the car is going, you would just give the speed, you just give 40 feet per second. And you know it's feet per second because that's what unit the original question is in. Now for part B, find how fast the angle theta is changing. We're going to put theta right here. So I'm just going to redraw the picture a bit. And again, feel free to press pause and solve this on your own if you would like. It's at the same moment as the last problem. So we know that dx dt is negative 40, dz dt is negative 32. We know that x was 16 and z was 20. And so to solve this one, we need a formula. This formula has to relate the angle theta somehow to the sides. And whenever you have an angle in these questions, you have to use trigonometry. Because trig is the only way to relate angles of a triangle to sides of a triangle. And you have your choice of like which trig function to use. Like you could use tangent, for example. Actually, that's sine. You could use sine, for example. But if you use sine, then we have both x and z. We have two functions of time, which means we have to use the quotient rule, and it just ends up being a more complicated problem for us. So instead, I'm going to use a function that avoids having to have both those in my equation. I want just one of those and the constant. So I could do, for example, tangent. Tangent of theta is x over 12. Or I could do cosine. Cosine of theta is 12 over z. I'm going to do tangent. But I could have just as easily have done cosine. But the idea is that we have a constant length, so we might as well involve it in our formula to make our life a little bit easier. The formula we really only use for its derivative. And then we just plug in our values. Now, dx dt we know. We got that from our previous problem, -40. d theta dt is the unknown value. For secant of theta, we don't know what the angle theta is, but that's okay, because we know that at this moment in time, z is 20 and x is 16. And we know that secant is just the reciprocal of cosine. And so cosine is 12/20ths, which means secant is 20 over 12. And so we plug that in. And then we simplify. This ends up being d theta dt is -6/5. And for the units, way back when we first learned the rules of differentiation for the trig functions, it all came from the basic trig limit. That basic trig limit that said that this value was 1. But this limit is only true if theta is in radians, which means all of our rules for differentiation only apply if theta is in radians, which means this must be measured in radians per second. So to summarize part B, any question about angles need trig functions, because trigonometry is the only way to relate the angles and sides of a triangle to each other. And if you have angles, you must be using radians, because all of our rules only apply if you are in radian mode.